Gibbs free energy and spontaneity. Welcome to an in-depth exploration of Gibbs free energy, the single most powerful tool for predicting whether a chemical reaction will occur spontaneously without external intervention. Named after Josiah Willard Gibbs, one of America's greatest scientists, this thermodynamic potential combines enthalpy and entropy into one unified criterion. When delta G is negative, a process proceeds forward spontaneously. When delta G is positive, the reverse is spontaneous. And when delta G equals 0, the system sits at equilibrium. In this presentation, we will derive the Gibbs equation, explore the four quadrants of spontaneity, connect free energy to equilibrium constants, and discover how biological systems harness coupled reactions to drive essential life processes. A spontaneous process is one that occurs without any continuous external driving force. Spontaneity does not mean fast. Some spontaneous reactions, like diamond turning into graphite, are incredibly slow. A non-spontaneous process requires continuous work input to proceed. The first law of thermodynamics tells us energy is conserved, but it does not tell us which direction a reaction will go. That is where Gibbs free energy comes in. At constant temperature and pressure, the most common conditions in chemistry and biology, Gibbs free energy G is defined as G equals H minus Ts. The change in free energy for a process is delta G equals delta H minus T delta S. This single equation captures the competition between energetic stabilization and entropic drive. The sign of delta G depends on the signs and magnitudes of delta H and T delta S, creating four distinct regimes. Quadrant 1. Both delta H and delta S are positive. The reaction is entropy-driven and becomes spontaneous only at high temperature, where T delta S exceeds delta H. Quadrant 2. Delta H negative and delta S positive. The ideal case, spontaneous at all temperatures because both enthalpy and entropy favor the products. Quadrant 3, both delta H and delta S negative. The reaction is enthalpy-driven and spontaneous only at low temperature. Quadrant 4, delta H positive and delta S negative. The worst case, never spontaneous at any temperature because both factors oppose spontaneity. This quadrant analysis is essential for industrial chemistry, where adjusting temperature can make or break a process. Temperature plays a decisive role in determining spontaneity when delta H and delta S have the same sign. The crossover temperature T cross equals delta H divided by delta S marks the boundary where delta G changes sign. Below T cross for an exothermic, entropy decreasing reaction, delta G is negative. Above T cross it becomes positive. For endothermic, entropy increasing reactions, the opposite holds. This explains why many endothermic reactions like ice melting become spontaneous only above a certain temperature. The T delta S term scales linearly with absolute temperature, so at sufficiently high temperature entropy always dominates. Industrial processes like the Haber-Bosch ammonia synthesis are designed to operate at optimal temperatures that balance kinetics with thermodynamic favorability. The standard Gibbs free energy change delta G naught applies to reactions under standard conditions of 1 bar pressure and 1 molar concentration. It is intimately connected to the equilibrium constant K through delta G naught equals negative RT ln K. When K is greater than 1, the natural log is positive, making delta G naught negative. Products are favored at equilibrium. When K is less than 1, delta G naught is positive, reactants are favored. When K equals 1, delta G naught equals 0. Each factor of 10 in K corresponds to about 5.7 kilojoules per mole change in delta G naught at 298 Kelvin. Tabulated values of delta GF naught for compounds enable prediction of reaction spontaneity without performing any experiments. Real chemical reactions rarely occur under standard conditions. The free energy change delta G under any given set of concentrations or pressures is given by delta G equals delta G naught plus RT ln Q, where Q is the reaction quotient. When Q is less than K, the reaction proceeds forward because ln of Q over K is less than 0, making delta G negative. When Q is greater than K, the reverse reaction is spontaneous. At equilibrium, Q equals K and delta G equals 0. This equation is arguably the most powerful in chemical thermodynamics because it tells us the direction of any reaction at any point. It explains why cells can synthesize ATP despite its large positive delta G naught of formation. They couple it to an even more exergonic process like glucose oxidation, effectively changing the reaction quotient to drive ATP production. Living organisms are master chemists that routinely perform non-spontaneous reactions by coupling them to highly exergonic ones. The most common energy currency is adenosine triphosphate, ATP. Hydrolysis of ATP to ADP and inorganic phosphate has a delta G naught of approximately negative 30.5 kilojoules per mole under cellular conditions. This exergonic reaction is coupled to hundreds of endergonic processes, from muscle contraction to protein synthesis to active transport across membranes, making them thermodynamically favorable overall. The principle is simple. If reaction A has delta G A greater than 0 and reaction B has delta GB less than 0 with the absolute value of delta GB greater than delta GA, then the combined reaction A plus B has delta G total less than 0 and proceeds spontaneously. This coupling strategy is the foundation of metabolism and is why ATP is called the molecular unit of currency in biochemistry. This comprehensive chart summarizes the relationship between delta H, delta S, temperature, and spontaneity. When delta H is negative and delta S is positive, the reaction is spontaneous at all temperatures. When delta H is positive and delta S is negative, the reaction is never spontaneous. For same-sign cases, temperature determines the outcome. The crossover temperature T equals delta H divided by delta S marks the threshold. Understanding these patterns enables chemists to predict and control reaction conditions for industrial, pharmaceutical, and environmental applications. Quiz question 1. Which statement correctly describes the criterion for spontaneity? Option A. A reaction is spontaneous if delta H is less than 0. Option B. A reaction is spontaneous if delta S is greater than 0. Option C. A reaction is spontaneous if delta G is less than 0. Option D. A reaction is spontaneous if temperature is greater than 298 Kelvin. Think carefully about the fundamental thermodynamic criterion before the answer appears. Quiz question 2. A reaction has delta H equals negative 80 kilojoules per mole and delta S equals negative 200 joules per mole Kelvin. At what temperature is it spontaneous? Option A, below 400 Kelvin. Option B, above 400 Kelvin. Option C, at all temperatures. Option D, never. Use the crossover temperature formula to determine the correct range. Quiz question 3. If delta G naught equals plus 15 kilojoules per mole at 298 Kelvin, what is the approximate equilibrium constant K? Option A, K approximately 1000. Option B, K approximately 0.0024. Option C, K approximately 1.0. Option D, K approximately 400. Recall the relationship between standard free energy and the equilibrium constant. Quiz question 4. For the reaction 2H2 gas plus O2 gas yields 2H2O liquid, delta G naught equals negative 474 kilojoules. What is delta G when Q is greater than K? Option A, delta G less than negative 474 kilojoules. Option B, delta G equals negative 474 kilojoules. Option C, delta G greater than 0. Option D, delta G equals 0. Think about the relationship between the reaction quotient and the equilibrium constant. Quiz question 5. ATP hydrolysis has delta G naught equals negative 30.5 kilojoules per mole. In a cell, delta G is about negative 50 kilojoules per mole. What does this tell us? Option A, the cell is at equilibrium. Option B, the ATP to ADP ratio is far from equilibrium. Option C, ATP concentration is 0. Option D, the reaction is endergonic. Consider whether cells maintain equilibrium or steady-state conditions. Problem 1. Calculating delta G naught from delta H naught and delta S naught. Calculate delta G naught at 298 Kelvin for the reaction C2H4 gas plus H2 gas yields C2H6 gas. Given delta H naught equals negative 136.4 kilojoules and delta S naught equals negative 119.8 joules per Kelvin. Is the reaction spontaneous? Step 1. Write the Gibbs equation with consistent units. Delta G naught equals delta H naught minus T delta S naught. Step 2. Convert kilojoules to joules. Delta H naught equals negative 136,400 joules. Step 3. Substitute. Delta G naught equals negative 136,400 minus 298 times negative 119.8. Step 4. Compute T delta S. T delta S equals negative 35,700.4 joules. Step 5. Complete. Delta G naught equals negative 100.7 kilojoules. Since delta G naught is less than 0, the reaction is spontaneous at 298 Kelvin. The reaction is exothermic, but entropy decreases. At 298 Kelvin, the enthalpy contribution dominates. Problem 2. Crossover temperature. For N2 gas plus O2 gas yields 2NO gas, delta H naught equals plus 180.5 kilojoules, and delta S naught equals plus 24.8 joules per Kelvin. Find the temperature above which this reaction becomes spontaneous. Step 1. Recognize the sign combination. Delta H is positive, endothermic. Delta S is positive, entropy increases. This is quadrant 1, spontaneous only at high temperatures. Step 2. Set delta G equals 0. T crossover equals delta H naught divided by delta S naught. Step 3. Convert units. Delta H equals 180,500 joules. Step 4. Calculate. T crossover equals 180,500 divided by 24.8 equals 7,278 Kelvin. Step 5. Interpret. Above 7,278 Kelvin, T delta S exceeds delta H, making delta G negative. This is why no formation requires lightning or high-temperature combustion. Problem 3. Delta G naught from standard free energies of formation. Calculate delta G naught for 2CO gas plus O2 gas yields 2CO2 gas. Given delta GF naught, CO gas is negative 137.2, O2 gas is 0, CO2 gas is negative 394.4 kilojoules per mole. Step 1. Write the formula. Delta G naught Rxn equals sum of products minus sum of reactants. Step 2. Sum products. 2 times negative 394.4 equals negative 788.8 kilojoules. Step 3. Sum reactants. 2 times negative 137.2 plus 0 equals negative 274.4 kilojoules. Step 4. Subtract. Negative 788.8 minus negative 274.4 equals negative 514.4 kilojoules. This highly exergonic reaction explains why co-combustion is so favorable. Problem 4. Relating delta G naught to the equilibrium constant. For N2O4 gas in equilibrium with 2NO2 gas, delta G naught equals plus 4.73 kilojoules per mole at 298 Kelvin. Calculate Kp at 298 Kelvin. Step 1. Write the relationship. Delta G naught equals negative RT ln Kp. Step 2. Solve for ln Kp. ln Kp equals negative delta G naught over RT. Step 3. Convert to joules and substitute. Delta G naught equals 4,730 joules. RT equals 8.314 times 298 equals 2,477.6. ln Kp equals negative 4,730 divided by 2477.6 equals negative 1.909. Step 4. Solve. Kp equals e to the negative 1.909 equals 0.148. Since Kp is less than 1, reactants are favored at equilibrium. The positive delta G naught confirms that the forward reaction is non-spontaneous under standard conditions. Problem 5. Non-standard free energy calculation. For 2 gas in equilibrium with H2 gas plus I2 gas, delta G naught equals positive 2.60 kilojoules per mole at 298 Kelvin. Let us calculate delta G under non-standard conditions. Step 1. Calculate the reaction quotient Q. Q equals pH2 times Pi2 divided by Pi squared. If we have pHi equals 0.50 atmospheres and both pH2 and Pi2 equals 0.01 atmospheres, then Q equals 0.01 times 0.01 divided by 0.50 squared equals 0.0004. Step 2. Calculate RT. RT equals 8.314 times 298 equals 2,477.6 joules per mole. Step 3. Calculate RT 1Q. ln of 0.0004 equals negative 7.824. So RT ln Q equals 2,477.6 times negative 7.824 equals negative 19,386 joules, which is negative 19.39 kilojoules. Step 4. Apply the non-standard equation. Delta G equals delta G naught plus RT ln Q. Delta G equals positive 2.60 plus negative 19.39 equals negative 16.79 kilojoules. Since delta G is negative, the forward reaction is spontaneous under these conditions. This makes sense because when product concentrations are very low, the reaction shifts forward to produce more products. This is Le Chatelier's principle expressed in thermodynamic form. Let us consolidate everything we have learned about Gibbs free energy. The master equation delta G equals delta H minus T delta S captures the competition between enthalpy and entropy. The sign of delta G determines spontaneity. Negative is spontaneous forward, positive is spontaneous reverse, 0 is equilibrium. The 4 quadrants of spontaneity depend on the signs of delta H and delta S, with temperature acting as a switch for same sign cases. The crossover temperature T equals delta H divided by delta S marks the threshold where delta G changes sign. Under standard conditions, delta G naught connects to the equilibrium constant through delta G naught equals negative RT ln K. For real conditions, delta G equals delta G naught plus RT ln Q. Biological systems use coupled reactions with ATP to drive essential non-spontaneous processes. From industrial ammonia synthesis to muscle contraction, Gibbs free energy governs the thermodynamic feasibility of every chemical transformation.